6.3, multiplication and division of rational numbers. So we're going to take a look now with our fractions, for the most part, right? That's how we're thinking about rational numbers for the moment, at how to do multiplication and division. And what I'd like for you to first talk about is just definitionally what it looks like, and then how it works from sort of a picture point of view. So if A over B and C over D are rational numbers that are then multiplied, then we simply multiply across the top, and we multiply across the bottom, and we all said, thank you for not making me find common denominators, right? Yeah, it makes these problems easier to work with, because I don't have to have common denominators. Okay, so what I'd like to show you is I'd like to show you a rectangular diagram of how this can be thought of and why it works the way that it does. When we hit fractions, kids are often very frustrated because all the way along they've been taught that if you multiply things, they get bigger. And now when they're working with fractions, that's not always the case. In fact, often when we're working with fractions, when you multiply things, they don't get bigger. And that can be very disconcerting. So this is a justification for why the answers become what they do. So go ahead and draw a rectangle. And I'd like for you to split the rectangle. We're going to represent the quantity 3 over 5. And just so that we're all doing it the same way, our pictures all match, go ahead and draw columns. So 5 columns down, okay? There's nothing special about the pictures matching, just it'll be easier for us to talk about it and to not kind of get confused. So I've got 5 columns. They should all be equally spaced. So imagine this is a cake, right? The first thing you do is you split the cake along this one edge, right? 5 of them. All right, so what we're going to do then is we're going to shade in 3/5. So 3/5 would be 3 of my 5 columns, right? So you go to party, and 3/5 of the cake is eaten, 3/5 of the cake remains. This would be the picture you have, right? You have 2 empty columns inside of the cake pan, and you've got 3 filled columns. Everybody good so far? And then you take this remaining cake to wherever you go next, and you're going to eat, quote unquote, 3/4 of it. So for the sake of what we're doing, go ahead and take the image you have and go ahead and draw horizontal lines. But go ahead and draw it through the empty space as well, because it'll make our process easier when we talk about the answer here in a minute. So you're just cutting along the other direction, 4 of them. So of the light blue that I have shaded, you have 3 columns and you have 4 rows, right? So if I wanted 3/4 of this picture, I would want 1, 2, and 3/4. Everybody good so far? So all I have left is the blue part, and I've divided it into 4 rows, and I've taken 3 of the rows and shaded 3 of the rows. So that's 3/4 of what was already there, just the blue part. So the part that's now still remaining is the yellow-blue double-colored, right? That's what's double-colored. How many boxes are in the double-colored region right now? There are 9. There are 9 pieces of cake, if you will, left right now. How many would there have been if I counted them all originally? How many? 20. So there's 9/20 that still remains, 9/20 that's double colored, however you want to think about this. And if you take a look back at the original problem, that's exactly what you get. Hang on. It's exactly what you get when you multiply straight across. 9 over 20. It's pretty cool, right? That's the picture. So I'd like to talk with you through a few different equality arguments, theorems that are present with multiplication. The first one is the multiplicative identity. 1 is the unique value such that 1 times any fraction is equal to that fraction times 1, which is equal to the fraction you started with. Multiplying by 1 doesn't change anything. It's an identity element. We also have multiplicative inverses as long as we're not dealing with the rational number 0. So if we have the number a over b, and a is not 0, then if we flip the fraction upside down, that flipped fraction is called the multiplicative inverse. It's the number I would multiply by my number to result in 1. So for example, if I had 3/4, what would I need to multiply by to get back to 1? 4/3. You can either look at this from the perspective of, oh, hey, look, if I multiplied across the top, I have 12. Across the bottom, I have 12. 12 over 12 is 1. You could also look at this from the perspective of simplifying across diagonals, which we'll do in a minute. If I look along this diagonal, these match, so they cancel out. And the same thing across the other diagonal. Again, we'll talk more about that in a minute. But this works also with whole numbers. Like, let's say, for instance, you had the number 5. Well, 5 is understood in a fractional form to be the same as the number, 5 over 1, right? So what would I have to multiply 5 over 1 by to get back to 1? 1/5, right? So it works with whole numbers, it works with fractions. We're just flipping the fraction upside down, and that's called the multiplicative inverse. It also has another name. We call it the reciprocal. You've heard that before too. We often use those interchangeably. So, all right. So a few properties of equality are next. The first one is distribution. The distribution property of multiplication over addition says that if I multiply by the fraction a over b times the addition of the two, that it's the same as multiplying it by each of the fractions individually and then adding them. Nothing different than you had when we did integers or whole numbers earlier on in this textbook. We had an addition property of equality last time, and now we have a multiplication property of equality. It simply says that if two numbers are equal, or two expressions are equal to begin with, and you multiply both sides by the same value, in this case e over f, right, that they will still remain equal. We use this in equations all the time. That's how you solve equations. One of the big components anyway. There's also multiplication properties of inequality. So inequality is when we have less than or greater than symbols involved. Technically, you could also have a not equal to symbol, but we don't usually group those together because they're dealt with a little differently. But when we have a greater than or a less than symbol, basically this is saying that if the number is positive, the direction of the inequality stays the same. And if the number is negative that you're dealing with, right, this e over f is negative, then if it was a greater than symbol, it's going to change to a less than symbol, and vice versa. You multiply by negatives, directions of inequalities change. And I usually show this in my number theory class when we get to this, but it makes sense and you know that it's true. So let me just show you a simple example. You know that 2 is less than 5. No problem, right? But if you were to consider -2 and -5, -2 is bigger than -5. And you could think about it from a perspective of a number line. Here's 0, here's -2, and here's -5. Being bigger means it's closer to the positive side or it's further to the right along a number line. So yeah, the direction changes when we multiply by negatives, and it's not simply just -1. It works with any negative value. It changes the direction of the inequality. And then the last one is multiplication by 0. It is exactly what you would expect. When you multiply by 0, you get 0. Not a very exciting turn of events, but it's true. So what we're going to do is we're going to use those properties to solve an equation. And on each step, we're going to identify which property we used. Okay? Why am I allowed to say that this step can happen? Justifying it. It's kind of like doing a proof. I know, you're really excited when I said that, weren't you? All you're doing is saying why you can do it, though. So on the first problem here, example number 2, it says 3/4 x equals 1/5. So what would be the first step to solving this? What would you do first here?
You just multiply 4/3 on both sides.
Okay, so you would like to multiply by 4/3. So how are 4/3 and 3/4 related? They're reciprocals. So the first thing we did is that we found the multiplicative inverse, right? The reciprocal. Okay, so that's step 1. We haven't actually really done anything. We've just written down that we're going to do it, right? We're going to multiply by 4/3. That's step 1. Step 2 is actually multiplying by it. Now, there's a couple of things you could do sort of in between here. You could say that we're going to regroup the 4/3 and the 3/4 together and leave the x out. Technically, that's what we're doing. That's called the associative property. So we haven't talked a lot about a lot of the properties yet, but that is what that one is. We're going to jump to the fact that when I multiply 4/3 by 3/4, I get what? I get a 1x, correct? I get 1x on the left. I know it feels even weird for us to write 1x because we assume just x when we do it, but really it's because it's a number 1. So the fact that I got the 1x here, that's step number 2. That's actually the multiplicative inverse property as well. Because the multiplicative inverse property said, when I multiply by the multiplicative inverse, I get 1. Now, on the right-hand side, what do I get? 4/15. So this is sort of like step 3, if you will, because the other side of the equation. And it has its own property, right? Or it's the definition of multiplication is what it actually is. We're almost done. The last thing is what you wanted to do already. It's to eliminate the fact that there's a 1 there at all. And the fact that I did that in step 4, if you will. Why is it that 1x is equal to x? Yeah, and that's actually a property as well. That's the multiplicative identity property. I don't think I'm out of line in thinking and saying that we take for granted all those properties all the time, don't we? We just know we can do them, but there's actually reasons behind why we're allowed to. So this is actually what's going on here. There's one other property I didn't mention, although I certainly could have, and probably should have. When I multiplied by the 4/3 on both sides, that process of doing something to both sides of that is actually the multiplicative property of equality, right? It didn't change the fact. If 3/4 x equals 1/5, then multiplying 4/3 on both sides keeps it equal as well. That's another multiplicative process, property of equality. Yeah, that's what it was, multiplicative property of equality. So there's that as well. All right, we're going to do another one. Got a little bit more going on in that one. This one rather than the previous one. Solve for x. Identify each property used in your solution process. So there's more going on here on this one because I got 2 fractions on each side, right? Kind of messy. And there's more than one way to solve the problem too. So I'm just going to open the floor to you. What would you do if you saw this problem as your first step?
Just do the second grouping of fractions. So left side of
You would do the 2x over 3 plus 1/4 or the other side?
the other side.
So you would do the x over 6 minus 1/2. So what would you do to the x over 6 minus 1/2?
I would focus on eliminating the half and multiplying it to 1/4.
Okay, so do you want to regroup things? Is that what you're thinking?
Yeah.
Okay, so that's one way to do it, right? One way is to get all the x's on one side and get all the constants on the other side. And you're going to have to do that eventually anyway, so we're going to go with Beth Ann's suggestion and we'll do that first. So the first thing I'm going to do is I'm going to move my x over 6 to the left, minus x over 6. and I'm going to move my 1/4 to the right by minus 1/4. And this actually is the addition property of equality. We saw it happen in section 6.2. And when I do this, I will now have 2x over 3 minus x over 6 equals 1/2 minus 1/4. Just repositioning everything. Okay, now all the x's are on the left, all the constants are on the right. What would you like to do next? Combine. So can you give me what would you do as an actual step, Brooke, for combining? Okay, common denominators, good. And if we're going to find common denominators anyway, we might as well find a common denominator for everything. Is that okay with everyone? So that I end up with two sides that are both the same, with the same denominator. It's not the only way to do it, but it's an option. I've got a 3, a 6, a 2, and a 4. 12. Does 12 work on all of them? Cool. All right, we will use 12 as our denominator. So that means this denominator gets multiplied by 4. This one gets multiplied by 2. This one gets multiplied by 6, and this one gets multiplied by 3. All right, and the interesting thing is that we're really doing is every single step that I just did, where I wrote those numbers next to them, I'm really just multiplying by 1. Everybody gets that, right? I didn't really multiply by 6 or 3 or 2 or 4. So the first one is actually going to give me 8x over 12 minus 2x over 12 equals 6 over 12 minus 3 over 12. And if we call this step 2, what we're really doing is we're multiplying by 1.
Wouldn't the 6 over 12 be negative? Because it was the 1/2 was originally negative?
Yes, thank you. I lost my negative. Definitely don't want to do that. Thank you.
So
Cool.
why are you multiplying by 1 and not the actual number?
You could, and you could eliminate the fractions immediately. We're just going to eliminate the fractions here in a minute. We talked about getting a common denominator, so they all have the same denominator now. They're about to be eliminated. Yeah. Okay, so on the left-hand side, 8x over 12 minus 2x over 12 is what? 6x over 12. And on the right, negative 6 over 12 minus 3 over 12 would be negative 9 over 12. And again, because they are both over 12, just like, is it Demi? Is that right? Just like Demi said, we really only have the numerators. The denominators already match. The numerators have to match as well. Okay, I've done lots of steps. Let's see here. This was step 3. We found a common denominator and we multiplied our values together. This was just multiplication. That's what this step was. Definition of multiplication, I guess, actually. And then on step 4 here, what do we do? We did what? Yeah, we combined like terms, right? That's as good as anything, I suppose. Okay. And then our 5th step here, how did we get 6x equals negative 9? One way to think about it is that we multiplied by 12, that common denominator that we found earlier. So it's multiplication is what it really is. What would I do next? Divide by 6 or multiply by 1/6 if you'd like. So x is going to be, this step right here is step 6. So again, that's actually a multiplication property of equality. because I'm multiplying by the same number, 1/6 on each side. What is negative 9 divided by 6 when we reduce?
-1 and 1.
You can write that. You could also write negative 3 over 2, like that. So you can change it into a mixed number if you want it in a mixed number. You can leave it as an improper fraction if you want to leave it as an improper fraction. What you can't leave it as 9 over 6 because it does reduce to one or the other, either the mixed number 1.5 or the whole or the improper fraction 3/2. So, and that step right there is just reducing. Or you can say it's simplifying or something like that would be fine. Okay, so I want to come back to something that Demi asked. She asked why we weren't doing something else at a different step. And the reality is there's lots of ways to solve this problem. So what I would have done if I were doing the problem, like for me personally, Demi, is I would have multiplied by 12 before I even moved anything from left to right. So there's lots of ways to approach this problem. Your steps will not necessarily match somebody else's. They should still all be legal and valid steps, and they should still have justification as to why they work, but they don't necessarily have to match some of the person's. Does that sound good? Okay. All right, I think I was trying to decide where's a good place to stop. I feel like this is probably a good place to stop because we're moving on into division after this. So let's pause here for today. We'll finish up with division tomorrow and do group work for section 6.3 tomorrow. But today we're going to move backwards and finish up section 6.2.